week 6. So we're talking about the inductive propositions chapter in prop. So the main focus in this chapter is showing how we can define properties and relations inductively instead of computationally or using some of the other logical connectives that we've seen before. So the initial example the chapter covers is talking about evenness of numbers. And so one way we can define that is using a computation. So something like the even b function, where it takes a natural number and returns a Boolean that says whether the number's even or not. So that's definitely possible for many properties that we want to define, but it's not always convenient because in this proof assistant, for example, we have to be able to show that even b terminates, and it may be for some properties it doesn't terminate, which means it's impossible to define, or it may just be hard to justify to the system that it does terminate. So that's one reason why we might not be able to do that. Another possibility is illustrated here, where we can define some sort of logical statement that says the number k is the number n is even if there is some other number that n is double k. So this is a more logical statement of the property as well. But what we'll focus on in this chapter is a third one, which is to use inductive definitions to define props. So we've seen quite a lot of inductive definitions for data structures like numbers and lists and things. And we've seen props like equality or exists or for all or and or. And this sort of combines the two into a single sort of thing where we can say it's possible to define what a proposition is inductively using cases and usually recursion and all that sort of stuff. So we'll see how that proceeds. So the example here is saying, well, we can define evenness inductively by saying, well, we know 0 is even, so that if you like, that's the base case of the induction. And a rule that says if we know n is even, then we also know essentially n plus 2 is even, SSN. And if we think about it for a while, we can see that the evenness of every natural number is captured by this definition, because we can apply the evenness of every even natural number is captured by this, because we can apply the EVSS constructor as many times as we like, and eventually we'll get back to 0 and we can use the EV0 constructor. Okay, so this is sort of similar to the argument that we can get every natural number by using the 0 constructor and the S constructor for the nat type. Except here we're going up in 2's essentially. One form of this sort of rule you'll see a lot in the literature and in this textbook is where we write these rules in a particular sort of graphical style. So they're often called inference rules, and we write them with a horizontal line, and above the line are the assumptions, the premises, and below the line is the conclusion. So this gives us a way of sort of summarizing the rule in a general sense rather than in a programming language or somewhere like that. So the EV0 rule here is saying, well, with no premises, in other words, no assumptions, you can conclude that EV holds for the number 0. Okay. And the other one is saying if we know EV of n above the line, that's an assumption, a premise, then we can conclude EV SSN. Okay. And this is a very common way to write down all sorts of things in programming language research. So in this sort of relation sort of property setting, but also, particularly for things like type systems and operational semantics, which we'll see later, of how a program evaluates is often written in this style as well. Okay, so now if we have these two rules written in their style, we can actually make a proof of that graphically. So we can sort of start with the thing we want to prove, which is EV4, and then we can use these rules, any that apply, to sort of work upwards to make a proof of the EV4. So in this case, the only one that applies is EVSS. So we can apply it to EV4, and that means the assumption is EV2. And then we can apply the rule again to EV2 to get EV0 as the next goal. And then we can use the EV0 rule to discharge that. So this is a linear proof, but in general, this will be a tree because inference rules can have multiple premises, so they branch upwards as we go. Okay, so in this case, it's just linear because the only rule with a premise only has one premise. Okay, so this is sort of the general idea. So the question is, well, how do we get this to happen in COC? Well, the answer is we just use an inductive definition of the style we've seen quite a bit before, except so in this case it's a property of natural numbers. So there's a parameter here which is the nat that we're interested in, and the output here is a prop, right? Just like all the props we've seen in the last chapter and so on. So there's two constructors that correspond to the rules that we've been using up here. So EV0 is a way of establishing that EV holds for the zero natural number, and EVSS has the parameter which is the natural number that is sort of 2 less, and a proof that that one is even, and then that gives us a conclusion that the 2 more than that is even. Okay, so as I say in this thing here, the ones we've been defining before have been types, right? In this case, this is a nat to prop. So what we're essentially defining here is a bit like a function. But the best way to think of this is a property of natural numbers, right? So if we can show that EVN is buildable using these constructors, then we say that the EV property holds of the number n. Okay. So one of the things that you need to sort of be clear about here is that the number here, this n here, is different from the nat that is the argument to the EV, right? So this is introducing an n that we can use for in this position, but the one in this position is a different number, okay? And so the signature up the top here tells you how many parameters every use of EV has to have, and where they come from is not forced. And in this case, one of them comes from another argument to this constructor, and in this case, this is a computed value from the n. Okay, so that's essentially what they're talking about here. So you can think of these constructors like EV0 and EVSS. They're just constructors, right? And they're essentially saying we can construct proofs of the EV-ness of something as long as we can apply these constructors together in a safe way. So for example, here we can say that we're trying to show that the 4 is an EV, which is essentially the proof we did before with the inference rules. And so we can basically say at this point, let's see if we can get this on the screen as well. Yeah, so we can look at we're trying to do EV4, and we can look at our constructors here and see which ones might apply. Well, EV0 doesn't apply, but EVSSN does. So we can apply it, and now we get EV2 as our assumption for that, and then we can apply it again, and then we can apply EV0 to that point, and we have no goals. So in some sense, what a definition like this is doing is it's providing essentially an axiom, which is the EV0 one, and a set of theorems, right? One for every possible natural number. Let's say if it's even, then 2 more than it is even. Okay, so we're essentially defining an infinite set of lemmas plus one axiom here. Okay, and that's similar to the reason why we like to do inductive definitions for types, is that we get an infinite number of things from a couple of constructors, or maybe a few constructors, right? So from a very simple finite recursive definition, inductive definition, you get an infinite number of data structures, like an infinite number of lists or trees or natural numbers or whatever it is we're talking about. Okay, so just like we saw in one of the previous recent chapters, is we can construct this proof in one go by just using the constructors with the appropriate arguments as constructor functions, just like the use of constructors to build other things. Okay, so this is essentially showing you that proofs are just objects, right? So this is constructing a proof made out of these pieces and applying it to use it as the proof of this theorem. So these are equivalent. The one up here is sort of using the tactics to do the construction part for you, whereas here you're sort of explicitly constructing the proof object by calling the constructors and then just applying it once at the end. Okay. Now, of course, we can prove other things. So, for example, we know that if n is EV, then n plus 2 is EV. That's one of the constructors, and we can use that to prove that 4 plus n must be EV as well. So I can proceed in the sort of way we expect, which is to introduce the number, and then when I simplify here, that gets rid of the 4 plus, just to make it a little more obvious what's going on with the s's. And now I can introduce the assumption that n is even. Now we have a goal that is just EV with some s's. So the only constructor here that applies is EVSS, right? Which is going to take off 2 of these constructors. Okay, we do that again. And then now we can use the assumption that n is even. EV. So that's pretty obvious, right? It's essentially if you already know that EVN implies EVN plus 2, then you can just do that twice to get to n plus 4. So that's essentially what this proof is saying. Okay. So in the exercise this week, this EV double is a homework, basically saying that you can show, using the double function that we had earlier, that every result of that function is EV, regardless of what the argument is. Okay, so I'll stop there. That's just a brief introduction to inductive propositions. We'll go on and use them much more in the rest of this lecture.